Hi, it's Dr. Brody. Throw on some headphones and let's dig into Chapter 6 on sensation and perception. I'm sure most of you have seen the dress. You know, the one that some see as blue and black and others see as white and gold. Yeah, me. I see it as white and gold. How can it be? I don't know if you've had arguments with your friends and family members over the dress, but this dress gives us an opportunity to think about why some people see it one way and others see it in a whole different way. Reality tells us that the dress is actually blue and black. And so by the end of this chapter, you should have a sense of understanding why all that argument actually happens, why some see it one way and some see it another. I find this chapter to be super, super interesting. There are so many things that we can look at that connect back to chapter 2 on neuroscience or chapter 5 on development. I think you're going to see a lot of these connections being made. When we talk about sensation, we're talking about a bottom up process where you're getting sensory information from the world, and then you are having to process it in your brain. That processing is a top down perceptual process. Normally, sensation and perception work hand in hand, but sometimes that's not the case. There's a condition known as prosopagnosia, and this is where you have sensation without perception. Can you imagine what that must be like? That means you get all of this incoming sensory information when you're looking at somebody, but you don't see the things as an integrated whole. We definitely take it for granted that we have sensation and perception so integrated, but there are some really fascinating examples of people where this is just not the case. As we're making connections to our previous chapters, think about Chapter 2 on neuroscience and what you learned about neural communication. In order for us to do anything, neurons have to talk to neurons, have to talk to neurons. And you learned about how they do that via the action potential. When we're talking about sensation in this chapter, we're going to focus just on vision. We're going to cover this because vision has been studied the most. And if you can understand vision, you can apply that knowledge to your other senses. When we talk about vision, the physical stimulus is light. As you learned in Chapter 2, we have to take that incoming information, code it, and transduce it into a neural response. When we're talking about light, that light is immediately coded for size, color, shape, and location. What's amazing is that this happens so quickly. It's transduced into this neural response, and then, if you remember, the occipital lobe is what manages the visual information. As humans, we can only see between 400 and 700 nanometers, and that's what's called our visual spectrum. It's kind of interesting if we think about what aren't we seeing? We're not seeing things that are beyond the 400 to 700 nanometer range. Things like ultraviolet light. Yeah, why do you think we forget to wear sunscreen? It's because we can't actually see UV rays. Bees, though, can see UV rays, but not our eyes. You need to be familiar with how you actually see both the mechanics and the structure of the eye and the visual process. When you're thinking about light as our physical stimulus, that light comes in through the cornea, passes through the pupil, then goes through the lens. The lens is then going to do something. It's going to change shape in order to perfectly focus the light on the back of the eye, which is the retina, the light sensitive area. The changing shape of the lens, that's called accommodation. The goal is to perfectly focus the image on that light sensitive area at the back of the eye, the retina. Some of you, like me, probably wear glasses. Think about that. Your glasses are an artificial lens. Maybe you're wearing glasses because your lens isn't doing what it's supposed to do. It's not perfectly focusing that image on the light sensitive area at the back of your eye. Maybe the image is focused a little bit in front of the retina, or maybe it's focused a little bit behind the retina, which means that your perceptual experience is blurry without your glasses. Glasses are such a great invention. For others, maybe it's not so much your lens, maybe it's the shape of your eye. Those of you with an astigmatism know that maybe your eyeball is a little bit more oval shaped than round, which makes it harder to focus that image on your retina. So you have glasses to help with that process. As you're understanding what happens as light hits your retina, you might look at the picture in the book and say, hey, that image on the retina is upside down. Correct. My question to you is, why is it upside down? And how do you then see the world right side up? This is a really fantastic question because if you think about it, when you're looking out into the world, you don't see people doing cartwheels and flipping over. You don't even have the perceptual experience of your vision being inverted by your brain. There are, though, these goggles that you can buy. They're called inverted vision goggles. I actually have a pair in my office. Come and see me. You can put these goggles on, and they will undo this process, meaning that the image that lands on your retina is right side up. You might guess what happens next. What does your brain do? There are lots of really interesting videos of people who wear these inverted vision goggles for a few days to a week, and you can see how quickly your brain adapts. It's pretty awesome. You need to understand that the heavy lifting of vision happens on that retina, the light sensitive area at the back of your eyes. This is where your photoreceptors live. Your photoreceptors are your rods and your cones, and they contain photopigment. They're doing the hard work. Make sure you know the differences between rods and cones. You should be able to answer this question that if you're walking in a dimly lit parking garage and somebody is walking towards you, what is helping you see the silhouette of that person? Is it your rods or your cones? There are also two theories of color vision in this chapter that I want to point out as something to keep straight. Color vision happens in two stages. You'll want to be familiar with the trichromatic theory of color vision. Trichromatic, think of three colors, three cones. The trichromatic theory of color vision helps us understand how we see traditional color TVs. There are red cones, green cones, and blue cones. Each of these sets of cones is maximally sensitive to a certain set of wavelengths. The combination of red light, green light, and blue light can create the perceptual experience of any color. This is what's known as additive color mixture. So with light, we can create the perceptual experience of a new color by varying the amounts of red, green, and blue wavelengths. When we're watching traditional color TVs, we're kind of tricking our brains, aren't we? When we see yellow, it's actually a combination of red and green. That's amazing when you're thinking about what our brain is doing and how we're then perceiving the world. The trichromatic theory helps us understand color TV. Three colors, three cones. We have another theory of color vision as well. That's the opponent process theory. The opponent process theory says that we have three types of color opponent cells: blue, yellow, red, green, and black, white. Basically, it's kind of a seesaw situation. If one half of the color opponent cell is on, the other one is off. So, like the red green pairing, if red is firing, 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 it gets kind of tired. And then green turns on. The way to demonstrate this phenomenon is to do what's called an after image test. There's a great example in their book where you're looking at a flag that is green, yellow, and black. When you stare at it for a long time, I mean long meaning about a minute or so, and then shift your gaze over to a white space, you'll see something kind of odd happen. In the blank space, you'll see a new flag appear, but now that flag is red, white, and blue. This is called an afterimage. It's kind of weird. There's actually no flag there, but you're seeing a flag and in new colors? This is because the green and the yellow and the black were firing, 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 firing as you were staring for a while. Those neurons got so tired that their color opponent partners turned on. What was green is now red, what was yellow is now blue, and what was black is now white. So again, opponent process theory, think after images, and trichromatic theory, three colors, three cones, TV. Since we're thinking about color vision, I want to give this chapter's spotlight to Dr. Christine Ladd Franklin. She was an experimentalist in the late 1800s, early 1900s, and she studied color vision. In her early life, she was told that excessive activity could jeopardize a young female's physical health and well being. She was basically told, yeah, don't think too hard, you're going to hurt yourself. Mm. Her work was really impacted by the exclusion of women in the field. Earlier in the course, we learned about E.B. Titchener's man only group, the experimentalists. Titchener was adamant that no women were allowed to join. He considered it very elite in a very man only space. Even though she was doing work that was very well regarded, she was excluded from these meetings because of her gender. She very famously wrote Titchener many letters criticizing his sexism and refusal to allow women in the room. She did have some support. She ended up marrying someone who was very supportive of her work, but the thing is, being married actually made her professional life harder. Married women were not allowed to hold academic positions. She had the support of William James, who we know as the father of American psychology and the person who wrote our first psychology textbook. William James thought Christine Ladd Franklin was very impressive, and it helped to have support from an insider for her to get her work out there. Because of this support, she was able to publish some really impressive papers despite having no academic affiliation of any kind. I mean, that's almost impossible now to do. She did a great deal of writing about her experiences and how she was so frustrated with her treatment in the field as well as other women. She wrote about men taking credit for her accomplishments, and that's a theme we see from quite a few of our early women scholars. She unabashedly fought for equality, and her fight did pay off. Fun fact, Christine Ladd Franklin, though not a member of the experimentalists because of Titchener, she was, however, officially the first woman to attend a meeting, a single meeting. She essentially crashed a meeting of the experimentalists after giving Titchener a heads up, a warning that she was just going to show up. Shortly after Titchener's death, two women were officially admitted and change started to unfold. So, Dr. Christine Ladd Franklin is someone to remember. She had a rough time in our field, but she did make contributions to our understanding of color vision and really fought the good fight so that our field could have more representation. Okay. As the chapter moves on, you get an appreciation for the amazing process of seeing and how quickly we're able to see and process information. I want you now to imagine being in a really crowded place. Imagine a really busy mall. You're in the food court, it's a Saturday, and you're going to meet your friend there at noon when everybody is going to be there. What do you do to find your friend? You start scanning, right? You're going to look around. It's crowded though. How long does it take you to know that someone is not your friend? Doesn't it seem kind of instantaneous? If you think about this, it's kind of amazing. We have parallel processing at work. Parallel processing means that we are simultaneously taking in all of this information and putting it together. In order to recognize someone, we're even adding another layer where we are comparing what we are seeing to all of our memories of that person. Parallel processing helps us see quickly and process information efficiently. It's frankly amazing that we ever find our friend. Even just the simple act of saying, hey, it's you, knowing your loved ones is a testament to how amazing and efficient and wonderful our brains are. So, as I close out this audio lecture, I hope you also have an appreciation for your own senses and how your brain and your sensory organs work together. Think about something as simple as throwing a ball to your friend. We know that there's a short delay with vision. In order for you to catch a ball that your friend throws, your brain has to account for the delay between what your eyes are seeing in what your hands have to do. Somehow, if you know how to catch, you're able to adjust for that delay. So, if you think about it, you're actually doing kind of a calculus problem and a physics problem when you're catching a ball. You are brilliant. So, if you, like lots of us, ever struggled with calculus or physics in school, just pat yourself on the back and remind yourself that not falling down the stairs every day means that you are kind of a sensory genius. Enjoy the optical illusions and other fun stuff in this chapter. Until next time.